Good afternoon, everybody. Thank you to be here. As always, in big numbers, and thank you very much again to be present at our in this our webinars from the channel MS Academy Lab. I want you to remind you that your microphone, your cam are off, and you are able to communicate with us through the chat and the Q&A session that it will be in the end of the presentation. I'm Matteo Mariani from Media System Lab, and today we are hosting Oxford Instruments, and the speaker will be Keith Dix, a very well-known expert in EBSD, and it will be I'm very sure, a great webinar today. I want to remind you to check daily our website, www.m-s.it, for new for the news and the next events that will be broadcasted in the next weeks. Again, please remain with us until the end of the presentation, because you will have the chance to ask questions to Keith directly. And yeah, enjoy the webinar, and I'll leave the stage to Keith Dix. Thank you very much.
Well, thank you very much, Matteo. It's a real pleasure to be able to spend a little bit of time chatting about EBSD, my favorite subject. I've been with Oxford Instruments for more than 25 years now, and most of that time I've been working on EBSD and have seen a lot of changes over the years. It's really become a very mainstream technique now, and what I'm going to be showing you is a bit of a snapshot, really, to just give an appreciation of what it is and what you can do with it, what it brings to the table. So let me see whether I can launch the presentation. Here we are. Okay, so I hope everyone can see this all right. I'm going to give a very sort of Jack and Jill explanation of what EBSD and how it works, and then look at the latest generation of EBSD detector and software, and explain some of the things that you can do with it. So what is EBSD? EBSD stands for Electron BackScattered Diffraction. This is the acronym for the technique. You will also sometimes hear people say EBSP, and by that they really mean EBSD, electron backscatter pattern. But these terms get kind of substituted, so you sometimes hear people say EBSD or EBSP. And it might sound a little trite, but it really is your eye into crystal structures, and that is quite literally. We'll see that in a few slides, that you are literally looking into the crystal structure, which is all that you're doing. And we collect the patterns that we can see from the crystal structure. We index them, as we call it, to determine the orientation, and then from that data we can derive all kinds of measures which give you information which is broadly similar to X-ray diffraction, and in some cases TEM. You can use it on any crystalline material, and what it really gives you is quantitative microstructure information. I say microstructure, it can be macro all the way through to nano. One of the big things about EBSD is it's a near surface analytical technique, and has inherently high spatial resolution, but you can use it from very low magnification all the way through to very high magnification without compromise. So it's very versatile and can be applied in all kinds of different areas. You can use it to develop new materials, control material properties, your manufacturing process. You can look at failures. corrosion, all kinds of different things, even reverse engineering to find out how something has been made. It's highly complementary with EDS, and we have this new detector which uses a CMOS technology, complementary metal oxide semiconductor type device, and we have called that Symmetry. And this will run at over 3,000 measurements a second. So you can see that we can collect data very, very quickly these days. So what kind of areas can you apply it to? Well, I'm sure you can read as well as me on this slide. The industries are listed down on the left there, on the left, just some of them. Obviously, it applies itself a great deal to academia and research, but it's increasingly relied upon in metals production, aerospace, nuclear, all of these areas where you need to know and control material properties very well. And that can be from making a better Coca-Cola tin all the way through to, you know, nuclear submarines and whatever else. You can apply this to anything that's crystalline, and so obviously that encompasses metals and alloys, intermetallics, also other crystalline materials like ceramics. Because it has very high spatial resolution, it's a very near surface analytical technique. It can be applied to thin films, and equally you can apply it to geological materials and others. You get a huge range of different measures that you can get. You can get an ASTM grain size measurement. You can look at the crystallographic texture for the whole thing or just a very localized portion. You can look at recrystallized and deformed fractions. You can look at substructure. You can characterize grain boundaries, look at strain, identify phases, look at phase distributions. If you've got a hot or a cold stage, you can look at phase transformations, and you can even use it to look at fractures and failures. So incredibly broad range of application. So EBSD, there's no getting away from it. There's a lot to do with crystallography. So I thought I'd search the internet and find some images relating to crystallography. And I found this rather nice example of a body-centered cubic unit cell, ostensibly for iron. This is 165 billion times larger than life. And it is, of course, the atomium in Brussels. And we frequently think about what we would call the unit cell, the indivisible, individual small part of the crystal structure, which defines the symmetry of the crystal. So this is body-centered. You can see that there's an atom in the middle, and that is providing bonds to all of the other atoms, and that makes for an inherently strong structure. So BCC metals tend to be harder and stronger, whereas if you don't have that atom in the middle, it's face-centered cubic, then that tends to be softer and more malleable metals, gold, etc., lead, whatever. Anyway, let's get away from looking at unit cells and instead think about a more realistic situation, which is that atoms are arranged in rafts. So here we see a model which has been made here by a Dr. Robert Crickle, and thousands of little red and white plastic or wooden spheres have been held together with metal rods, and he's had this built into a gigantic cube. And the first thing that you really notice about this when you look at this is that there are visible bands or planes in the crystal, very, very visible indeed. You can see this all the way through that structure. And in fact, if you get a bit closer and take a picture with an ordinary camera, you can actually see the similarity here between this plastic sphere model and a real life diffraction pattern. So for instance, if I took this into Photoshop and made it black and white and then decided to make it rather blurry, you can see how the electron backscatter pattern is actually formed. We're actually looking into the crystal structure of the material, and this is why I say it's your eye into the crystal structure. You can literally see the arrangement of the crystal lattice, and you can do this at any magnification that you want, low magnification or high magnification. All that's happening is that the beam is entering the sample, becoming scattered. The diffraction will be behaving in accordance with the Bragg equation, n lambda equals 2d sine theta. Theta is the angle of incidence, and because the electrons are scattered within the lattice of the material near the surface, you find that you essentially illuminate all of these different planes, which then radiate out electrons that fall on the phosphor screen and generate the diffraction patterns that we see. So each of these bands in the pattern is called a Kikuchi band, after the Japanese researcher who first reported seeing these bands. And the symmetry of the crystal is reflected or given in the symmetry of the pattern, as is the orientation. So if you twist the crystal one way, the pattern will twist in the same direction. So if we can just find a way of detecting the bands and indexing the pattern, to use a phrase from X-ray diffraction, then we have a means of analyzing the sample. So the first thing that we would do is we detect the bands using a mathematical transformation. This is called the Huff transform, and this particular transformation will render bands or lines in an image as a series of bright points on a fairly anonymous background. And the effect of that is that we can look for those bright peaks in Huff space, and then we can know by working backwards through the equation where the bands must have lain in the pattern, and thus we can know the position and the angles between them. So once we've got all of those angles, which we list in a table, we can then compare that with a table that we make for the actual crystal structure that we want to analyze. And when we find a match between the two, we can draw an overlay over the pattern, which shows graphically whether or not we've indexed it correctly. So this is a visual aid to be able to decide whether or not we've got the correct solution or not. So it's commonplace to see these overlays on patterns as a means of judging whether it's correctly indexed. So let's have a look at what's actually happening when we're scanning across the sample. I've made a schematic view of the sample containing a number of grains. These grains have got atoms arranged in different orientations, and as the beam moves across the sample, when it crosses into a new grain, we see a different diffraction pattern, and when it crosses into a new grain, we see another diffraction pattern. So as we scan across the sample, we're going to be picking up these different patterns, and we'll be applying the band detection and the indexing to each as we go along. So how do we get from these patterns to orientation results, and how do we display those in some convenient way that we can easily visualize? So one of the things that we use are various color keys. In this case, it's the inverse pole figure color key, which fortunately is more or less triangular, and we can apply false color to that. So we have colored that space with red, green and blue. And the effect of that is that when the beam falls into one particular region, such as a 110 type orientation, which would be down in this region of the figure, then we're going to pick up a green color, and we're going to display that green color or that pixel in the map as green. Equally, if we fall into another region which has got a 100 orientation, which is going to be towards the red end of this figure, then again we'll color the pixel that relates to that red. Similarly, if you have a 111 orientation, we're going to fall up in the top corner of the figure, we're going to find blue, and that's the color that we're going to draw into the pixel. So all orientations, not just the three that I've mentioned, we're going to pick up some sort of color somewhere between red, green and blue. So you can see in the bottom right hand corner that we get directly from the diffraction patterns to visible maps that contained color pixels, which give you an immediate indication of the orientation, or at least the plane which is parallel to the surface of the material. One of the things about EBSD is that we get a huge amount of data in the form of orientation measurements in a spreadsheet, and we can use these to get various orientation maps and also misorientation. So if we look at the difference in measurements or orientation between neighboring pixels, we can use that to learn something about the strain condition of the material. We can also look at grain size and boundary types. We can identify different phases. We can look at strain, and there's a huge number of other measurements that we can get from this. And we supply an advanced post-processing algorithm, which we've called AZtec Crystal, which allows you to extract the various measures and plots, graphs, diagrams, maps from your data set, and there is a huge wealth of information contained within the data set. Well, let's have a little look at the detector itself. We have this new detector which we have called Symmetry. It doesn't actually detect the symmetry of the crystal itself. It's just a name. We've had this since May 2017, and it's the world's first CMOS-based EBSD detector which doesn't have a lens in it. It's fiber optically coupled. And this we'll see later is an extremely important aspect, that we get a far more sensitive detector by getting rid of the lens. We also use a custom designed CMOS sensor, not one that you get off the shelf, and we can get up to over 3,500 measurements a second. We can have a whole range of different resolutions, and we see them on the side here. So you can see, for instance, that if you want to go over 3,000 measurements a second, you can still maintain 156 by 128 pixels. And we'll see that that gives a really quite good looking pattern, which we can index extremely well. And so we can apply these high speeds to all of the material jobs that you would ordinarily want to encounter, not just the easy stuff. We can also tilt the detector, and this means that we can have the phosphor screen at different heights. That means that we can work at any working distance that we like. So we can have very large samples in there and very long working distance, or if we need very high spatial resolution, we can have very short working distances. We also have a proximity sensor, which means that we know when an accident is going to happen at the phosphor, and we can retract the detector out of the way. So if the stage is being moved too close, the detector will suddenly retract out of the way. We also have a handset or little keyboard that you can operate as well if you like that. So here's a schematic showing what's going on. The sample is tilted at 70 degrees. Now that might be either on the stage or using a pre-tilted holder. It's entirely academic which you use and which suits your purpose best. The reason why we have to tilt the sample is that this maximizes the contrast and the intensity in the pattern, and that's a matter of physics. We don't have much control over that, so we always have to tilt the sample up. That usually means that we use dynamic focus on the microscope and tilt correction so that the image appears as if it's zero tilt. And then you can see from the shape of the front end of the detector that we can get the EDS detector in nice and close at a variety of different working distances. We've also got imaging detectors arranged around the phosphor screen. Two above, these give essentially a backscattered signal with atomic number contrast, as you can see in that image. Or in the three lower detectors, we are imaging forward scattered electrons, and these carry orientation and topography contrast. So we can see that you've got a different kind of contrast in that image below. And on the phosphor screen itself, we have the diffraction pattern. And you can see here that we've got quite a a large solid angle of the pattern visible there. We've got a number of different zones, which is where the bands intersect, and this is providing us with a very good pattern for indexing. So this is an example of a forward scattered electron image. This is in black and white. You can also have it in color. You can, by applying red, green and blue to those three lower detectors, you can get a false color image. And here you can see that there's a large number of grains which are recrystallized with twins, and you can also see a region over towards the left with a more mottled appearance. This is some strained regions, so this clearly is a partially recrystallized piece of material. And this image is obviously a great prelude to performing EBSD, because you can already see what's going on in the structure to help you decide whether this is a good spot or not for your analysis. So let's think a little bit about the actual detector itself, what makes it better than others. On the left here, you can see at the bottom, there's a rendition of a charge-coupled device, so-called CCD, and to the right of it, you see CMOS. And what you find is that a CCD device is a serial device, and that basically means that all of the pixels that make up the imaging array have to be read out sequentially in a series, and then when you get to the end, you can go back to the beginning and read out again. So this means that it is inherently a slow process to read out a CCD device. And also the architecture is such that the charge to voltage conversion and amplification is done off the imaging array, and that acts as a bottleneck as well. Now the CMOS device, this is an entirely different type of semiconductor architecture, and each of those imaging wells or pixels has the charge to voltage conversion actually within each pixel. And then a number of vertical columns on this diagram can be read out sequentially. So in this case, we've drawn it that all of these vertical columns are being read out and subject to amplification before they leave the chip. So all of the analog to digital conversion, the charge conversion is done on chip, as is the amplification, and there's many parallel registers which are read out simultaneously. So this makes for a much higher speed device. And this means that even at relatively high pixel resolutions, 156 by 128, we can see that we can achieve 3,000 measurements a second. In fact, up to 3,500 measurements a second. So it's this that really gives us the advantage that we can use this for all materials and still achieve very high speeds. Maybe not always the maximum speed, but we can certainly achieve very high speed. And because we're not using a lens, and we'll see more about that in a minute, we're able to do this at comparatively low beam currents. So in this particular example, this is the patterns that are shown there are done at 10 nanoamps. So let's consider the previous generation of detector. So this is a cross section through a Nordless or Norloose detector, and we can see at the front end of the detector we've got the phosphor screen. We can see more or less in the middle you've got the lens, and then at the back you've got the imaging array, the CCD. So for all of the light that's emitted at that point, only a relatively small proportion of it is going to actually fall on the lens and pass through the lens. So a relatively small amount of light is going to actually pass through the lens. So we've got a low collection efficiency at the outset, and there's obviously going to be losses through the lens itself, which means that even less arrives at the CCD itself. So the phosphor screen, typically you're going to get something like 10 to 20% efficiency, 10%, 15%, something like that, of electrons will be converted into photons, depending on the striking energy. Your sensor is going to be about 70% efficient, but the lens has got really very, very poor transmission characteristics. And that's because all of this light that's being emitted in a hemisphere from the photoelectric event that's taken place here at the Phosphor, only a very small proportion within that cone of light is going to go through the lens. So this really is not a happy situation. We see that we've got very low collection efficiency because of all the light that's emitted. We only see a tiny proportion of it, even when we use very exotic lenses like an f/0.7. And in that last generation of detector, we actually had specialized lenses designed and made to achieve these very low f numbers. But even so, the improvement in the collection efficiency was really quite minor. Now, if we go to fiber optics, which have been used in many low light applications and particularly in night vision goggles, etc., you can appreciate that by coupling whatever it is you want to look at through a fiber optic bundle down to your imaging device, then you can get a much higher transmission or collection efficiency. And you can see here that it's laid on top of a dollar bill, and you can see a magnified image there because of the difference in the sizes between the front and the back. So let's have a look at this in use. If we consider that same event at the Phosphor screen, now we're seeing that a very high proportion of the light is contained within a single fiber, or maybe a number of fibers that obviously are closely associated with each other, and these would be conducted through the bundle and then delivered, if you like, to the CMOS imaging array. So this has got inherently high collection efficiency, and this is going to lead to a much more sensitive detector. So if we look at this schematically, you can see that when the sample is struck by the beam and the phosphor fluoresces with the diffraction pattern, then we directly conduct that image, if you want to use that term, down onto the imaging array. We lose very little of the light along the route, and because of the many parallel registers, we can read that device out very quickly. So this gives us both very high collection efficiency and potentially very high speed as well. So let's have a look at a few examples just to give us an idea of what's going on here. This is a nickel superalloy. We actually guarantee 3,000 measurements a second using 12 nanoamps, although we can usually do much better than that, so that's what we guarantee. In this case, this nickel superalloy was indexed at 3,000 measurements a second, more or less, and we've got a 99% indexing rate for only 4 nanoamps, and this is at 20 kV. So you can see that we've got really very good sensitivity. Here's a more difficult example, a titanium alloy. Here we've managed 3,500 measurements a second, 98% indexing, but we've used rather more beam current here, 20 nanoamps at 20 kV. Let's see what happens if you go the other way. Well, here we are at 5 kV, which is an incredibly low striking voltage. And here on a nickel superalloy, we've been able to run at 200 odd measurements a second with a 99% indexing rate at 5 nanoamps. And this is at 5 kV. So that really gives an indication of the sensitivity. So let's have a look at the sensitivity, which we have described as patterns per second indexed per nanoamp as a measure of sensitivity. So if we look at a standard CCD type detector, you see the numbers there under sensitivity on the right hand side in black, and then to the right of it you see the dose required for a similar but lens coupled CMOS. So if you're using a lens coupling, you get a variation there in the sensitivity, which is not as good as you would like. So I think it's fairly evident that using the fiber optic coupling is the important aspect here to achieve the kind of sensitivity that you want to get. Here we see the phosphor screen moving up and down so that we can get to long or short working distances to suit the acquisition geometry. We can also do simultaneous EDS by choosing an appropriate working distance. We've got motorized insertion, a bellows vacuum seal. We've got active collision prevention with the proximity sensor. It's always calibrated and ready for use, so there's auto calibration. There's auto exposure, so you don't need to think about the settings for the camera in terms of exposure, and we also automatically correct for background, so you don't have to collect a background, and a very wide range of operating speeds. So here we see a little video which I'll just click on, and what you will see in this video is that someone types in a movement for the stage which is going to drive the stage until it actually collides with the detector, and we'll see that in fact the proximity sensor detects the presence of the sample and quickly reverses out of the way. So this is collision prevention. It's not a touching alarm, which frankly isn't much use to you really, because I think you normally know when you've had an accident. So having a buzzer sound isn't really a great help to you. But clearly being able to actually retract out of harm's way before the accident happens, then this is a great advantage to see it again. Okay, so let's have a look at the effect of adjusting the height of the phosphor screen. Here we see a diffraction pattern which is not so great at the top, pretty good at the bottom, and we see that the phosphor screen is at its 0 position. If we play this video, we'll see what happens when we move the phosphor screen. We can also see that we've got no EDS counts at this time either. So what we're going to do is we're going to open up the dialog to adjust the position of the phosphor screen. We're going to move it to -8 millimeters. Then we see the phosphor screen move and the pattern comes up on screen. And we also see that the count rate for the EDS comes up because we now have line of sight to the EDS detector. Then we can click on the sample and it indexes. We didn't have to do any re-indexing. It's good to go. This is because it's always automatically calibrated. If we look at what the results would have been like with the phosphor screen where it was, we get about a 92% indexing rate. And when we move the phosphor screen, we get about a 97% indexing rate. If I move here to have a look at that, you can see that some regions have not indexed as well as they could have done. That's because the pattern was rather low on the screen. But when we move to the phosphor screen so that it's in ideal collection geometry and you've got the pattern nicely centralized on the screen, then we can see that we get this virtually 100% indexing rate. So let's see what this means for us in practice. So it might seem a little perverse, but I'm going to show you an EDS result to start with. And this is actually a steel boiler pipe which has got a layer of corrosion on the surface. And if you perform EDS on that, it's not terribly surprising to find that the corrosion product is both iron rich and oxygen rich. So I think we could have guessed that really. We can see that there are two obvious distributions. So maybe we've got two different oxide types here, but it's not clear to us exactly what those oxide types are. We have no idea really. We just know that there's iron and oxygen rich layers within that corrosion layer. So if we look at this in a bit more detail, here's the electron image of the sample. I'm afraid I've enlarged this from a brochure or a technical data sheet, so it's a little bit pixelated, but you can see the image there with some little particles and the different layers. And if we look at the iron, we can see the distribution of iron. There's some quite higher iron content here, lower, and then a sort of intermediate amount. If we go to the oxygen, again, we can see at least two populations of oxide there. But I mean, that's as far as it goes. You can't really say much more than that. Now, if you do EBSD, suddenly you've got much better spatial resolution, and because these different oxides are crystallographically very different, we can easily tell them apart. So we're not just looking at elements now. Now we're actually looking at compounds. We're looking at the FeO, the Fe2O3, and the Fe3O4. So now we actually know what different oxides we've got, where they are, and how they relate to the corrosion mechanism as it's progressed. We can see that the grains are columnar. We can see these little individual pockets, and this is actually quite a blurry image because again it was clipped out of a brochure. So if you see this in real life, it is really very, very sharp indeed. And we get this spatial resolution from EBSD because the escape depth of diffracted electrons is only about 20 to 50 nanometers. So we get an inherently much better spatial resolution from EBSD under the same conditions as EDS. So let's have a look at some cracks in a sintered nickel alloy. So I mean, here we can see that it's a polished sample. There's a crack that sort of staircases here through a grain and then follows some different paths. Yeah, it'd be interesting to know what's going on there. So the first thing we can do is we can look at the orientation information. So we can see that this is a 100 oriented grain where we can see that the crack isn't able to propagate straight across it. It has to follow certain planes. When it gets into a 111 oriented grain, it's able to progress at a particular angle. But again, it's not so easy to understand exactly what's going on here. We'd like to know something about what's happening in terms of strain. So if we choose a different color key, and in this case it's called kernel average misorientation, this is where we look at the misorientation between neighboring pixels in a small kernel or box of pixels, and we move that across the image so that we can scan out, if you like, those areas which have got higher degrees of strain compared with those which have got lower amounts of strain. We can see that there's high levels of strain associated with the 100 oriented grain and much lower levels of strain when it's propagating through particular planes in particular orientations of crystal. We can also see that in the region here at the crack tip, we can actually see there are two cracks which appear to be coalescing, and we have these tendrils of strain reaching out from one crack to the other. So we're able to see something very interesting about the manner in which this crack has propagated, far more than if we just, you know, look back at, let me go backwards, use the keyboard. Here we are. So when we see this just as an image, it's not very revealing, but as soon as we see the orientations and then the strain fields associated, we can learn something about what's going on here. This is a different color key called disorientation coloring, a subtly different approach. And here we see that the colors are rather different. And that's the nice thing about EBSD. You can pick and choose the color key that you want to apply to something to suit your purpose. This is a nickel superalloy. This is 3,000 measurements a second, about 6 nanoamps, 99% indexing rate. And here you can see that most of the grains are recrystallized, but there are a few large grains here which haven't recrystallized. It's a partially recrystallized structure. Here's another example of kernel average misorientation in a nickel superalloy, and you can actually see these. It's a very highly strained material. You can see these networks and packets of strain and very high levels of strain associated with the crack tips and near the cracks themselves. This is just a high quality diffraction pattern to show you the sort of quality that you can get from the detector. For elastic strain measurements, we can generate very high quality patterns which can be used in software to find very low levels of strain. Here we're actually looking in transmission, so we can actually do EBSD in transmission. We call this transmission Kikuchi diffraction, but it's essentially all the same detector hardware. It's just a special holder that you can put a TEM grid or sample in, and then that mounts it above the phosphor screen so that the beam can strike the sample, which can be at 0 tilt, and then we collect the emerging diffracted electrons on the underside that fall on the phosphor screen. We have a special indexing algorithm that corrects for the distortion in the patterns and correctly detects the band centers and gives, as you can see here, a very high quality result. And this is on an aluminium alloy, which has got low atomic numbers. So generally the quality of patterns from aluminium, there'll be fewer bands visible than in, compared with a higher atomic number. This is a geological sample, and you can see here a range of different crystal forms with some low symmetry in there. So it's not just the easy stuff that we can do. This has a fantastic indexing and band detection algorithm, so we can work on the most difficult materials and get really excellent results. So to summarize, I've been chatting for about 40 minutes. The big thing here in using CMOS in this detector is that we have developed fiber optics. It took us about 5 years to develop, but it means that we get the highest possible sensitivity. It's software controlled in terms of insertion and detector position, the tilt. We've got the proximity sensor. We use a custom designed sensor for EBSD, not an off-the-shelf, and it is an all-in-one detector. It's both sensitive and fast. So it excels in every application, and the Symmetry Fibre Coupled CMOS is far superior compared to any type of lens-coupled CMOS detector. So we can achieve 3,500 measurements a second. We can do that at very modest beam current. We can do high resolution EBSD, as I mentioned, for elastic strain. We've got the tilting and the proximity sensor, and we have the integrated 4 scatter detector. So we can have a quick look at the software itself. I won't spend too long on this, as I think we're more or less at time. But we'll give you an idea of how easy it is to use the software, the workflow, and just get a general idea. So this is the user interface where we can see an index pattern. The beam has been positioned on a portion of the sample. We can see a diffraction pattern there. We can choose different indexing modes. We have 3 different indexing modes, and we can see the details for our chosen phases at a glance so that we can decide what settings to use. It's very quick, and you can actually watch the data building up in real time. Here you can see EDS maps at the top acquired simultaneously with the EBSD data beneath, and you can have pole figures and inverse pole figures being populated as you acquire. You've also got a navigator approached guide, if you like, through the process. You're guided through step by step what you need to do. So it's not really the sort of toolbox of yesteryear where you had to know what to do and how to operate it. You're led through by the hand. You know what to do next. You follow the steps. You can't go wrong. Also, the system is automatically calibrated. We do this when we install the equipment, so we do it for a series of different working distances and a series of different detector insertion positions. This means that we can create a giant lookup table of all the different parameters, so that whatever working distance you're at and wherever the detector is, in terms of how far away from the sample it is, we look up the correct values for the pattern center and the detector distance, and it is in calibration. So earlier in the presentation, when I showed moving the phosphor screen, you can just click on the image and start indexing and collecting data. You don't have to go off and recalibrate anything like that. It's all automatic. You can define the collection geometry at the outset. You can also add notes, etc., which are ready to be taken into the reporting steps. As we've seen earlier, you can have these different images. And here you can see that by this little red chevron, that these three images are being used to create this composite image. So you're able to pick and choose which images you want to actually work with. And you can even, using this arrowed functionality here, generate false color. So here we see something in black and white, or we can see it in false color by applying red, green and blue to the different segments of the detector. We've seen that we can move the phosphor screen up and down, so I don't think we need to dwell on this one terribly long. We can also choose between single pass indexing, opt to special very clever band detection, and single pass indexing. We've called this Optimised TKD, but you can use it for EBSD as well with great effect. And then we have iterative indexing, where we index it more than once, making minor movements to the band positions and band shape so that we can reduce the residual error, and thus arrive at the smallest possible residual error, the highest possible angular accuracy. So refined accuracy allows us to get really very high quality data. This TKD mode, we can see the Huff transform here. Here we can see a very broad band. These narrower bands will come out as single peaks. This very broad band will come out as a double peak. So if we use the standard Huff transformation or Huff band detection, and we compare that with the TKD mode, we're going to find here that if we use the standard indexing mode, we pick just one of the edges, whereas when we use the TKD mode, we'll see that we actually correctly identify the middle of the band. So this is very important. This TKD mode is a greatly improved band detection method, and means that when you've got very broad bands, which might happen when you're doing TKD, or when you're working at very low kV, for instance, we showed 5 kV, we can get very good band detection and very good indexing. And as I say here, we can use it for EBSD, not just TKD. We have very reliable indexing. So, I mean, here's an example with an apparently 100% indexing rate or hit rate, but in fact, these regions here are just randomly indexed. Really, they should be blank. Better, I think, is to only index that which indexes within certain parameters. So in this particular case, these regions have not been indexed at all because they do not belong to the phase that we have indexed. This is silicon or silicon oxide, whatever. This looks like copper metallization to me, with some through silicon vias, and you see that we've only indexed the regions of interest. We haven't indexed all of this other stuff. So it's far more important, I think, to index correctly rather than just get a very high hit rate and then try to sort it out afterwards with some kind of confidence index. Okay, I've mentioned about refined accuracy. I don't think we've got time to go into it in great detail, but in general, we can get angular accuracies down to about 0.01 of a degree, when normal EBSD might be somewhere in the range 0.1 to 1, typically about 1/4 of a degree. So if we look at using refined accuracy, here we got a very highly deformed aluminium alloy on the left, if I remember correctly, and here we can see the kernel average misorientation map, where we can see all of these strain networks. And if we look at one of the regular indexing modes, TKD mode, nearly 3,000 measurements a second, but if we use the refined accuracy mode, the iterative indexing, it goes that much slower, but the quality of the data is phenomenal. We can see all of these strain fields. We've also got chemistry assisted indexing. So if you've got two crystal structures that are essentially very, very similar, you might well get regions where it's a bit of a muddle, but you can apply the chemistry. Here we see a niobium rich area, and we've been able to correctly identify this region. We can also do large area mapping, which means that we can set up a large area and map through it with many maps. And this means that we can have apparently very low magnification. Here you see 5 millimeters. So there's lots of things that we can do within AZtec EBSD that gives you all of this flexibility for all of these different sorts of applications. We're looking here at phase identification. This is where we can take an unknown compound on a Martian meteorite. We can determine the chemistry. We can acquire a good pattern for it. We can look at the chemistry and decide on some ranges that we're going to search a database for. We can find some candidates which we then index for, and we now find this is olivine. So we can use this phase ID to identify unknown phases. As mentioned previously, we've got the live data viewing, which means that as you're acquiring the data, you've got a good idea of what's going on. So to summarize, it's very flexible and versatile. It's very fast. You can collect at up to 3,500 measurements a second without necessarily compromising your data integrity. It's very user friendly. You're led through the process with a navigator, and it's very reliable. We don't return data up into the spreadsheet unless we're very satisfied with the indexing. And we can take this through to our post-processing without having to clean up the data before we can use it. Generally speaking, the amount of filtering that's applied to data is extremely minimal, if at all. So that takes me to the end. A good 50 minutes, I think. So I'm happy to answer any questions that you might have put through. So back to you, Matteo.